Hi guys, Luke here, and I'm here to talk about organocuprates, which are effectively Grignard reagents stroke lithium RLI groups as well. However, whilst the RLI stroke Grignard reagents are a lot harder nucleophiles, these are a little bit lower order, and you can form them like so. Low order cuprates are formed using CuBr or CuI and RLI. And this forms copper in the middle, attached to the lithium with our two R groups from the 2RLI. The high order more reactive cuprates are formed from the cyanide version of the above, the copper cyanide, and instead of binding to the lithium, this actually binds to the side that keeps bound to the cyanide and removes the lithium altogether, and just has two lithium plus on the end, which means the copper is 2 minus here. So we can use these organocuprates in conjugate addition, and here's a comparison of our conjugate addition with RLI or our Grignard reagent and our organocuprate. As you can see, this goes through a 1-2 addition, 1-2 conjugate addition for our Grignard and RLI groups. So effectively the R will attack at this position. As you can see, we've numbered these 1, 2, 3, 4. Whereas our organocuprates, they prefer to go for a 1-4 conjugate addition instead, and obviously attack at this bond here. That shifts over to there, etc, etc. As you can see, the product there itself. So the uses for this, it's used in alkylation. As you can see, another indication of the 1-4 conjugate addition. THF used once again. Like I said, that reagent's used for quite a few of the organic reactions we're doing in this course. Pretty much a simple reaction there. The O minus donates there, forms a double bond there. Double bond, that should be an arrow from the double bond there, should attack that double bond. That pushes the electrons onto there, and then the bromine can leave, acts as an electrophile. And then the stereochemistry is important to remember as well. Obviously, a larger group will prefer to be on the opposite side to another larger group in inverted commas of methyl. Here's another example for an intramolecular molecule. So this is in a molecule that's already combined, sort of thing. Obviously, this can be any form of alkene here. It doesn't have to be cyclic. But the same thing happens again. It goes 1-4. We form this. As you can see, nothing really changes there. We've got the methyl group, obviously, that came from our organocuprate. The minus charge can come down, and the double bond can come across to form another bond here, which connects the two together. And then the O can move up there as well. And then once that's happened, we've got our product. The methyl and the H on the same side here. The larger OH group is facing towards us, and the methyl group, which is effectively this group here, has sort of rotated sort of up there, and that's facing behind us as well. We know the hydrogen faces behind us in this case here because we need a small group there, even though we've only got hydrogen anyway, so we know that anyway. Cuprates have plenty of uses, which we're going to go through pretty much all of them right now. Might as well while we're on copper complexes. They can also go displacement of alkyl halides and pseudo halides, which is a tosyl ligand. RLI and the Grignard undergo side reactions, which we saw as well on the lithium halogen exchange, where there's deprotonation or elimination. So if you don't know what they are, definitely go back and watch the other videos. And as you can see, cuprates can cleanly displace the alkyl halides or the pseudo halides. As you can see here, it can displace iodine, chlorine, bromine, or our tosyl or triflate ligands, I suppose. Not ligands, but groups from this straight away. So all it does is just donate that. That binds to there, and I leaves pretty much. It's just an SN2 reaction. And epoxides can also be opened cleanly. This is also an SN2 reaction. Basically just attacks straight away, so the ET attacks there, removes that, and then on workup we get OH. Nothing too difficult there. Whereas for the Grignard case, there's a sort of 1,4 addition in this case, where we don't cleanly get rid of it. We can't go straight away for an SN2, it's more like an SN1 sort of thing, and we have to form double bond there instead. There's a bit more on cuprates, and then we're pretty much wrapped up. And then I think next time we move on to silanes, Silanol and stuff like that. So there's TF2. I've drew it twice. That's the way we learn it in one lecture series. That's the way we learn it in another. We'll see that on the other lecture series soon, most likely. So we've got a cyclic ketone. We're going to add TF2 to it using a base, excuse me, ET3N. The triflate sits nicely on the O there. So I think what happens is something attacks there. We move up to there, and then electrons move over there as well, and the triflate can just bind straight away. Next up, we've got our effectively R2. So this can be R1, this can be R2. This is a harder nucleophile in this case. You know what, I'm going to actually write for a change. So we can call this R1, if the pen works. That could be R1, and that can be, my bad, that could be R1, and that could be R2. So that reaction undergoes as it would. We attack in at the double bond, and then we push electrons out onto the ester group there. That forms a minus charge this time rather than a double bond. It could easily form a double bond as well, because then we just push the double bond back and remove the OTF group. And then, as you can see, the product forms as you'd expect. Double bond forms there. OTF's been removed, and that just leaves us with the product that we added from our cuprate up there. It can also be done in the addition to alkynes, similarly to the Grignard. Very, very similar. Attacks the triple bond. We get CuLi in the middle rather than just Li this time. And yeah, that's a shortened version. Try and add that to effectively what we had in this method here, and we pretty much just get the same what we had last time. That's basically showing us that we can add one side, I suppose. So what we do is just add one of those sides. It's like, I'll get my pen again, why not, because we're here. This can effectively be classed as R2. So we've got, in other words, CuLi, excuse my drawing, should be a BU there as well. We'll get down to that in a sec. If you can't see that right now, you can sort of see it. So we've got that there, and then we've got BU. That can go all the way down there, attack there. That can go up to there. That can go up to there. And then that can just come straight back down, like that. That's effectively what we've got. And that forms a product there, and like I said, there should be a butyl there as well. And finally, I think this is the last point, it can be used in SN2-like reactions, which we pretty much saw earlier. As you can see, one of the R groups comes in, it displaces this group here, and opens the epoxide ring as we saw in one of the earlier methods using copper. That forms this product, and it will form, obviously, it will form that. So it will form, where are we? Here, plus R, CuLi, and that effectively. That's what it will form. Just double check, see if we've finished cuprates. Yep, so we're pretty much finished. Actually, there's a little bit more left, but I think what we'll do is leave that for now because we're talking about more heteroatoms. Still using copper, but we're using heteroatoms. So I think I'll leave it there. The next time we're going to talk about lithiation to heteroatoms, and this will hopefully be a shorter video. And then the time after that, I think we move on to silane. So thanks for watching, and I'll see you on the next video.